back up. Okay, all right. Welcome to Lecture 5 in Steel Design. Homework 1.2 is graded. I think by and large it went fine. It was largely just a scavenger hunt within the manual. The purpose of that homework was, again, just to get you to open the book, because as you saw in lecture last time, and for the homework that was due today, you're going to be opening the manual, and I don't want the manual to be something to be scared of, because it's not. It's a straightforward, easy to navigate resource once you get used to it. So let's talk about what we need to cover today, which is basically taking our concept of net area, and we want to expand on it a bit. What we did last time was we assessed gross and net area for paths that were what I call parallel. And parallel maybe isn't the best adjective, but grid-like patterns is what I'm talking about. And so if you remember, we had developed sort of a rough conceptual formula for the net area. And we said that the net area was the gross area minus the area lost due to the presence of bolt holes. But really, if I was being, I don't know, a bit more scientific, I might write the formula like this. The net area equals the gross area minus the sum of the bolt holes, which is the diameter of the hole times the thickness. And remember, the diameter, we use an effective hole diameter. We take the bolt diameter and we add 1/8 of an inch to it. Why do we add 1/8? Because we're adding 1/16 twice. 1/16 of an inch we account for erection tolerance. We actually drill the hole physically larger than the diameter of the bolt by 1/16 of an inch. And then we add another 1/16 of an inch to account for that little ring of damaged material that we don't really consider effective in transferring stress to the entire tension member as a whole. Now that formula is fine and it will work. You could spreadsheet that formula if you'd like, if the bolt patterns are parallel, if the bolt patterns are grid-like. The problem is this, okay? So if you have a connection that looks like that, where the bolt patterns are staggered, okay? So it's almost like sort of like this honeycomb type thing, or they're staggered. That formula is not enough. We have to change that formula a little bit, and I'll show you how we do that here in a second. But we talked about this near the end of class last time. What we do in here is very real world. This is realistic stuff, and I say that knowing that sometimes, it feels like what we did in structural analysis was very theoretical. This virtual work, compute the deflection, unit load stuff, and then these moment diagrams, which are these, theoretical constructs. I get that sometimes it feels like a math or physics class, but this is very real world stuff. And if I ever introduce something to you that seems a little strange, I always want you to know there's a reason for it. So why do we do this? And we talked about this last time, because it increases the net area. That by changing the pattern of the bolts, you can increase the area of the member. And increasing area is a way of making it stronger. If sigma equals P over A and you have the same limiting stress, then by increasing the area, you can increase the P, increase the load that the member can withstand. So there is a reason for doing this. Now, when we deal with a staggered bolt arrangement, there are two complications, and we're going to handle each of these one at a time. Okay, the first is, how do we account for the increased area along the diagonal failure paths? Because instead of, and I'll sort of draw this over here, instead of just, before when we would load a tension member that cross-sectional would go like this, now we're going to have cross-sections that, I don't know, that didn't work out. Maybe we're going to have a cross-section that does that, or something like that. So we're going to have these diagonal failure paths, and how do we account for those little diagonal sections? That's going to be something that we have to talk about. We also are going to, as we're going to see here in a second, have a possibility of multiple failure paths. That it's not just one section that we need to look at; it's multiple ones. And part of this, and you're going to see patterns, and later on you're probably going to go, well, why did we need to check for all of these? Couldn't we just check for the one that was the worst case scenario? There are reasons for me wanting you to identify all of the possible patterns, and that'll become clear as we progress through some lectures. So just bear with me up until now. We'll get there. Now, one of the things I want to clarify is that whenever we identify failure paths, we want to identify failure paths based on what's called the lead line of bolts. And so I have a tension member. So imagine we're taking this tension member and we're yanking on it. That is the worst arrow I've ever drawn. So we're yanking on it, you know, sort of like this. You can see I've got some staggered bolts, and some of them are highlighted yellow. So the easiest way to define that is if we're talking about the connection, the yellow bolts are all the ones that are closest to the inside of the member. Those are the lead line of bolts, okay? And there is a reason why we only consider those, and I want to just show you that from a common sense standpoint. So let's say, for the sake of discussion, that this is my tension member. It's just a little sheet of paper here, and I'm yanking on this tension member, okay? So let's say I've got it sort of like this, and I'm holding it in my hand here, okay? And I'm yanking on it. Okay, so again, this is sort of the gross section, if you will, and this region over here, we're talking about, you know, my net section. If I'm yanking on it, think about like where this piece of paper would rip in half. You know, it could rip in the middle, in the gross section, but let's say we were talking about the net section near the connection. Where would it rip? I think most of you would probably agree that it would probably rip, you know, if I'm holding it like this, it would probably rip sort of like near the end, like where my fingers are, right? Near this far end of the connection, like it would rip near the end. It wouldn't rip sort of in the middle here where I'm gripping it. It would rip, you know, on the exterior. If I go back to the slides, you know, imagine that tension member is sort of a sheet of paper. If I'm yanking it, the failure paths where that is going to fracture in half are really going to be the ones that fall along this outer region here. Does that make sense? The lead line is always the line of bolts that are closest to the inside. Anybody have any questions on that? Okay. All right. Now, what we have to do, one of the complications we're going to have to consider is recognizing. Is this also true with compression members? That's a really good question. So the short answer is no. And I'm giving you sort of a weird way of saying no, and I want to tell you why. Number one, whenever we get to compression members, the entire game kind of changes. The reason why is compression members, we're not worried about yielding or fracture or anything else. Compression members do something much different than tension members. Compression members buckle. And so to put it in perspective, and I'll actually throw some numbers at you so that you can kind of see what I'm talking about here. Let's just have some fun with this. Okay. Let's pick a section. Let's just have some fun with this. Let's pick a, I don't know, 12-foot long, I don't know. Let's do W14 by 82. W14 by 82, that's 12-foot long, can probably hold up about 1,000 kips in tension under yielding and about 880 kips in tension under rupture. But if you compare that to the compressive, the buckling, what was that, a 14 by 82? 14 by 82. So let's see. So if we compare just the yielding, and we compare that to the buckling capacity, you'll end up seeing that the buckling capacity is far less than that. I think for the numbers I said, if I'm reading that right, I think we're looking at, I don't know, like 584, 562, something like that. So the capacity is far less. Here, Well, okay, Mr. Spiraczynski has a good question, and we're gonna cover that here in a second. I really want to address that. But the easiest way to sort of go about Mr. Ball's question is to just look at this from a physical standpoint. If you ever have seen like an old wooden yardstick, if you take that wooden yardstick and you press it in compression, it fails at around like, I don't know, 5 or 6 pounds. But if you yank on it in tension, it'll fail at, I mean, it takes like, a couple 100 pounds to snap that thing in half. So the whole concept of yielding and fracture and whatnot, and what we're talking about here, doesn't really affect a column. It can, however, affect the connecting elements. So if you have a column connected to a beam and you have some plates that are being used or some angles that are being used to connect one element to another, then those elements you might have to consider yielding and fracture, but you really wouldn't handle them any differently than what we're talking about here, as you'll see here in a bit. And I don't want to obfuscate it too much. It'll probably make a little more sense once we start digging into the class. But just long story short is we really don't have to consider a lot of this stuff with columns, and that'll become clear later. And Mr. Spiraczynski asks, why would the middle of the member not be considered for failure? The short answer is it is considered for failure. So what we end up doing later, so right now we're considering gross and net area. What we're going to do once we've sort of tackled that and tackled this concept of shear lag, which we're going to talk on Monday, we're going to start doing tension member analysis. And in tension member analysis, we're going to consider both cross sections. We're going to consider the gross section and the net section. For each one of those sections, we're going to compute a capacity. So there's going to be a capacity in the gross section and a capacity in the net section. And if we want to express how strong that member is, we're going to take the lowest, the one that governs. If I yank on it, which is going to happen first. Mr. Randall, is a fracture critical member just any tension member? Oh, you're throwing out some bridge terms there. All right, so fracture critical. I can talk about fracture critical all day long. The term fracture critical is a dirty word of bridge engineers, I guess you could say. But basically, and I'm going to use my language here specifically, a fracture critical member is an element in tension in a bridge that is perceived to cause systemic level failure if it fails. It's not always systemic level failure, but it's perceived. So if the idea is if you have a truss and a tension member and that truss fails, then the whole truss collapses, that member would be fracture critical. It is a dirty word among bridge engineers because we try and avoid fracture critical systems. If we do include fracture critical systems, they have increased inspection requirements and so on and so forth. It's not to say you can't use fracture critical systems, but there better be a good reason for doing it, like economics and so on and so forth. But it's mostly a policy and inspection level issue than it is a net area issue, if you will. So yes, I danced around some of your questions, but we're gonna, everything that you talked about, maybe with the exception of Mr. Randolph's question, we're gonna kind of cover in one way or another throughout the semester. Any other questions? Because this is good stuff. I like this. All right. Okay. So I want to talk a little bit about, and I'm going to keyboard off here because I kind of need the tablet here. All right. So I want to talk about possible bolt paths. So one of the issues that doesn't happen with a grid-like pattern that happens with staggered patterns is that when you're trying to compute net area, there's multiple possible ways that the member could fail, okay? Multiple possible paths. So let me give you an example, all right? I've labeled some of these bolts and some of these edges with letters here just so that we can all speak the same language. And I'll walk you through one. When you're identifying bolt failure paths, the idea is that the paths will always be perpendicular to the axis of the member unless there is a diagonal component, okay? So, for instance, one of those failure paths might be this one. This would be path BDG. All right. It would, that path, if I was trying to find the net area, I would have one hole and I'd have no stagger. Okay. Another one might be this path. So perpendicular, except for when we cross diagonal bolt lines. So the member might separate this way. So this would be path, I don't know, A, C, D, G. Okay, how does that differ from the previous path? Well, the previous path had one hole. This one goes through two holes. But looking at the diagonal path, you know, there's an increase in net area right here. There's an increase right there. So that increase in net area means we have to account for one staggered path. All right. Now I'm just curious, can anybody identify any other paths? Is there anything else that you see that might be a potential path that we got to consider? A, C, D, E, F. So bam, 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 bam. This one has three holes, but it has two staggered paths. And again, notice that all of the bolts that I'm using here, all the bolts are lead line bolts. They're the ones on the end, right? Right. Remember the idea of the lead line, that they're always the ones there on the end, because the brake line is over here on the right. So the main body of the member is going to the right, going over here. All right. One of the things that I want to get away from this is just your ability to identify those paths. Now, I wrote down path A, C, D, G. What about B, D, E, F? Well, assuming that the member is symmetric, B, D, E, F would have the same net area as A, C, D, G. Now, it's possible that the member isn't symmetric and that those net areas might be different or might have some changes there. I'm going to show you an example maybe a little bit later where it is a very real possibility that they wouldn't be symmetric based on the member geometry. We might do that later when we start doing some full-blown tension member analysis. Right now, I want to take it one step at a time. Now, what we do for this is, and I want to be clear, the idea of failure along a staggered path it's actually pretty complicated from a mechanics standpoint. Like, in order to determine the stresses and the areas, because your failure path is diagonal, and you also got bolt holes there which cause stress discontinuities, that's actually pretty complicated from a mechanics standpoint. You really have to roll up your sleeves to do the mechanics. So how do we handle that in the real world? One of the things that you're going to start to have to get used to in sciences like steel design, and it's not just steel design, but you'll find it in concrete, you'll find it in foundations, you'll find it in hydraulics and environmental, is sometimes we as engineers encounter problems that are tough. They are not easy. And if you tried to start deriving formulas, you really couldn't do it. All right. This isn't like a moment diagram where you can derive, you know, WL squared over 8. Sometimes the mechanics are so complicated that there is no nice, pretty closed form equation that we would like. But it doesn't change the fact that we still have a problem and we still need to deal with it. So what we'll end up encountering or end up using is what's called an empirical expression. We use an approximation, something that captures the situation, captures the issues closely. It's probably not 100%, you know, accurate, but it's close enough. Okay. And the advantage of what we're seeing here, the stagger factor, is that not only is it close enough, but it's easy. Okay, it's not this incredibly long, fourth order differential equation. It's a little term, and it'll work for our purposes. So that being said, how do we handle a staggered bolt path? Anytime that we have a diagonal path between two bolts in our net area, we add what's called a stagger factor. And the stagger factor, we add that because if you have a diagonal path, you're increasing the area. So anytime we have a diagonal path, we increase the area by adding the stagger factor. And the stagger factor is computed as S squared over 4G times the thickness. So you've got the thickness, and then you've got S and G. S is the longitudinal spacing, and G is the transverse spacing. So if the load is going left to right, S is your left to right dimension, G is your up and down dimension. G is perpendicular to the applied load, S is parallel to the applied load. That's the more general expression. Now, if you actually look up the language in the spec, this section B4.3b on 16.1-20, you'll find that the T actually isn't listed in the spec. The T, it just says S squared over 4G. But the way the spec says, or the way the spec is written, you add S squared over 4G for each path, but you still have to multiply by the thickness to get an area. So that's why we have the area thrown in here. So let me go to that other slide here in a second. So a more complete expression for AN would be for bolted connections. If we want to compute the net area, we take the gross area, we subtract all of the bolt holes, so the diameters of the hole times the thickness. And remember that we take the diameter by taking the bolt diameter and adding 1/8 of an inch. But then we add any necessary stagger factors. And so the stagger factors would be S squared T over 4G. Okay. Now, one of the things that we actually haven't talked about is welded connections. What if instead of bolting a member to, bolting two members together, what if you're welding them together? Well, if you aren't removing any material, like if you're just doing a fillet weld, then the net area equals the gross area because there's no bolts, So, and we have a whole, I think, week or so where we're talking about welded connections. So don't worry, we'll give welded connections their time in the spotlight. Now, the only other thing I want to clarify before we get into our example, let me go back here, is a note on the stagger factors. So when you're computing stagger factors, I wanted to make this connection. I wanted to look at this connection just to illustrate what we're talking about here. Let's say that we're considering this failure path. Okay. This failure path would go through 1, 2, 3, 4, 5 bolt holes. So the way that we would compute the net area is we would take the gross area, we would subtract 5 bolt holes, but what we would do is we would add up 4 stagger factors. Okay, we would not take one big stagger factor with one big S and one big G. We would take 4 little stagger factors for each of those paths. See, the stagger factor is S squared over 4G, or S squared T over 4G. So you can't take one big S and one big G and then it be equivalent to 4 stagger factors, each with their own S and little g. The math doesn't work out that way. You have to account for each diagonal path separately. So you'd have a stagger factor, for this, a stagger factor for that, a stagger factor for that, and a stagger factor for that. 4 different stagger factors. Does that make sense? Okay. All right. So what I want to do is I want to go through this example. Okay, so we're going to compute the net area for this plate. Now, the plate is 1 inch thick. 3/4 inch diameter bolts are used. So right off the bat, if they're 3/4 inch diameter bolts, what's the diameter of the hole going to be that we're going to use? There we go. We're learning stuff. We're cooking with fire. Okay. Now, I want to mention a couple of things about the diagrams here. Number one, we are actually, because of the way that this connection is proportioned, we're actually going to compute multiple net areas. We're not going to compute one, we're going to compute a few. And so from each of those net areas, so we're going to have, I think, at least 3 of them. For those net areas, we're going to compute all of them, and then we're going to take which one controls. And so we'll talk about what that means here in a bit. The other thing I want to mention is every now and then you're probably going to start to see stuff like this where I don't put the dimensions everywhere. I might just say typical TYP. And so that just reduces clutter on the schematic. So if you ever see that, that's what that means, just abbreviation for typical. Because one of the things I do want to try and introduce you to is some terminology. That one's easy, but we're also going to look at some welding symbols and things like that so that if you see them, you can kind of know what you're talking about. If you've ever seen welding schematics, they can get crazy real quick. They get a little out there. Okay. All right. So let me see. I think yesterday what we ended up having to do was actually just share the entire notebook. So I'm actually going to do that on Blackboard because I want this to be clear. So share. I want to make sure this is clear. Okay. Let's make this full screen. All right. So we're going to compute the gross area and the net area for this, although, I mean, the gross area is pretty easy. I'm going to make this image a little bigger just so that everybody can read the dimensions. Okay, so remember, we have a formula. So our new formula is the gross area minus the sum of the bolt holes plus the sum of what we'll call our stagger factors. And remember, stagger factors are just S squared over 4G times the thickness. Okay, so let's go through a couple things. Let's start off with the gross area. Okay, so what is this dimension right here? Twelve inches, that's right. Okay, so this is 12 inches. So what is the gross area? Just to, I mean, it should be pretty easy, but I want to make sure everybody's paying attention. There we go. It's 12 inches times the fact that we have a plate that's an inch thick, 12 inches squared. Okay, so we've got that. Now, 12 square inches, there we go. So now let's look at the hole diameter. I know we already put that in the chat, but I'm just going to put it here so we have it. So the bolt diameter is 3/4 of an inch. And so we said the hole diameter was 7/8 of an inch. Now, one of the things I want to go ahead and see if we can compute, and we have the luxury of doing this because the section is symmetric about the horizontal axis, but let's look at our stagger factors. So we have an S, a G, and a T. Now we know the T is 1 inch. Can somebody look at some of these diagonal paths? So we're sort of looking at, you know, like these diagonal paths here and those diagonal paths there and whatnot. Can somebody look at these and tell me, like, what are the what's the S value? What's the S value going to be for one of those diagonal paths? Let's see if anybody remembers what the difference between S and G is, and what's the diagonal path going to be? Or sorry, the S value. Sorry, the S value. There we go. So S is 1.5 inches, and G is going to be what? There we go, 3.5 inches. So what we can do is we can say, so let's do a couple things, okay? So let's look at net area. Because I'm going to try and be a little efficient on this. So here's our formula. Let's go back to our formula. So our formula says that it's the gross area minus the sum of the diameters times the thickness plus the sum of the stagger factors. And I kind of like writing it this way because if you remember on the homework that you all just turned in, we had a rolled shape and there were bolts that went through both the flange and the web. So each of those bolt holes had different thicknesses. But in this instance, all the bolts are going through a common thickness. So what we can do is we can just say, let's just compute DE times the thickness, which is 7/8 times 1. So that's just going to be 0.875 inches squared. Well, let's also go ahead and just compute the stagger factor. So what do we have here? Does anybody have an answer for this? $0.161. All right, do I have a second on that? There we go. And keep in mind, what are the units? There we go. So whenever we do a stagger factor, again, when you look it up in the spec, it's just S squared over 4G. We have to add that thickness so that it's in square inches. Okay, that's kind of important. Okay, now here's what I want everybody to do. Okay, I'm gonna put some labels on this. Let's use our red pen. So A, B. Now remember, this is the lead line computation. So these right here, those are the lead line bolts, right? The brake line is over there. That's the brake line. So remember, those yellow bolts, those are the ones that are on the end. Those are the ones that, you know, if we grip it, that's where we're going to have our fractures. So we'll say C, D, E, F, G. Okay, so somebody read a path off. Somebody give me one.
A, D, F.
All right, so let me scroll down here a little bit. So path number 1 is A, D, F. Okay, how about another one? B, C, D, E, F. Okay. What about another one? Do we have another one? B, C, D, F. Is there another one? B, C, all right. Now, I want to talk about B, C, E, G for a second. I want to talk about that. Now, Mr. Ball mentioned BCEG that goes through the lead line of bolts. And that is true. That's a possible path if something is considered, and we're not gonna consider this path in here. And there's a reason why. If so remember, let's go back to that example of the thumb, me gripping the paper with the thumb. BCEG would be a path that would assume that this front bolt has already sheared in half. So not like if you were to separate that member and the member would fail, not only would you have to shear through BCEG, but you'd have to shear that front bolt in half. Because think, if the member separates and this part of the member goes off, then that front bolt has to shear as well. So we're not going to consider connections where the front bolt shears. You can do that, but I'm going to tell you, number one, it never governs. And later on, we'll talk about why. When we get into bolted connection land, we'll get into that. Because in bolted connection land, we're actually going to look at the bolts, or we're going to look at the shear capacity. So for now, we're not going to consider any paths that would sort of isolate the bolts on the other side. Does that make sense? So we're not going to consider BCEG, but I want to see, just from a symmetry perspective, if there's any other path that we're leaving off. See, I'm actually glad you brought that path up, Mr. Ball. Well, we said BCDF. What I'm getting at is there a mirror image of that? Like, what about A, D, E, G? What about that? Oh, okay. Now, Mr. Romans, I get what you're saying, ACDF. Okay, that's a good question. Like, why not this path? Why not ACDF? But think, the only reason that a diagonal path would happen is, think about the physics of it. The only reason that we'd ever encounter a diagonal failure path if it was between bolt holes. Like if you're ripping this thing in half, why wouldn't it just fracture perpendicularly? You see what I mean? And think, like, even if you did account for ACDF, yeah. So is path 2 wrong? No, path. Oh, yeah, that should be. You're right. You're absolutely right. It should be B, C, D, E, G. Yeah, you're right. That is correct. I didn't even notice that as I was writing it down. You're absolutely right. It should be B, C, D, E, G. That's exactly right. All right, I will say this. I'll go ahead and spoil it for you. There aren't any more, but I do want to make sure that everybody understands sort of the method behind how you identify them and why we're not considering BCEG. Because if you fractured through BCEG, that D bolt would sort of be left off hanging. It would be shearing. And again, we'll handle the bolts and their shear capacity entirely, in their entirety, but we'll handle that part later. Right now, I'm just interested in the limit states that leave all the bolts intact for now. All right. Any questions? All right. Let me ask you a question. Let's take path number 1. How would you compute the net area on path 1? Somebody tell me how you do that. You could turn your microphones on. I won't bite you. How would you calculate the net area of path 1? I'll scroll up a bit. How do you do that? That's ADF.
You just take the area and subtract the D hole from it?
Yeah, just subtract a single bolt hole. So we would take the gross area minus DET. So that would be 12 square inches minus 0.875. And that would be, what is that, 11.125? Yep. All right. Okay. So all right, somebody else. All right. Now let's talk about the second failure path, the BCDEG. Somebody help me out. How would you compute the net area of that? What would you do? So you take the gross area. What do you do? All right, well, let me ask it this way. Well, let's look at it a bit more systematically. Let's go back to our formula. This is our formula right here. The gross area minus the area loss due to bolt holes plus any necessary stagger factors. Now, we're talking about B, C, D, E, G. Okay, this is the path that we're talking about here. So help me out. We've got the gross area. Tell me what to do. How many bolt holes do I subtract? 3. Now, what about stagger factors? What about the stagger factors? What do I do? Somebody help me out. So you're telling me I take the gross area minus 3 bolt holes, but then what's the formula say? The gross area minus the diameter of the hole times the thickness plus stagger factors. So do I add stagger factors? And if so, how many?
2. You have 2 stagger factors.
There we go. There we go. So our second net area for this second path, this BCDEG, is the gross area minus 3 plus 2 stagger factors. So 12 minus 3 times 0.875 plus 2 times 0.161. Does everybody see how I'm doing that? Well, I'm saying something's up there. That it's not that big. .9 or sorry, 9.697. All right, I'm gonna get to your question in a second, Mr. Romans. Do I have a second on this value? Okay. Now, Mr. Romans asks, how do you know how many stagger factors there are? Okay. Look at the path. Okay. So first off, let me erase this up here on the connection. Okay. Let's be clear. We're talking about this path right here. We're talking about path BCDEG. Okay. So go to your connection and draw that out. What does BCDEG look like? It looks like that. That's the path, right? You see that I drew that up there on the connection in purple? So how many bolts did I go through? I went through 1, 2, 3 bolts. To answer your question, Mr. Romans, how many diagonal lines did I draw? There you go. No word. This is the stuff I like to hear. This is good stuff. Now let's draw. So for path number 3, I drew them together, right? I said B, C, D, F, and A, D, E, G. Let's draw the first one. Okay, so B, C, D, F is B, C, D, F. Okay. How many bolts am I going through? How many bolt holes? All right. And how many diagonal paths did I have? How many staggers? 1. Okay. So if I wanted to compute that net area, I would take the gross area minus 2 bolt holes plus 1 stagger factor. $10.41. Do I have a second on that? Okay, good deal. Now, all right, let me ask you this, okay? Before we sort of conclude the problem, that was path B, C, D, F. Is there really any difference between B, C, or sorry, A, D, E, G, right? Draw path A, D, E, G, and then ask yourself, how many bolt holes? It's going to be 2. How many stagger factors? It's going to be 1. So there's no difference, right? It's symmetrical. It's symmetrical along the longitudinal axis of the member, and even just from a math perspective, it's the same number of bolts, same number of stagger factors. Nothing changes. That's why those two paths are kind of the same. All right. So now we're at the end of the problem, and you're asking yourself, okay, we got 3 net areas. What do we do with them? Okay. All too often in steel design and in structural design in general, we tend to compute a lot of different values, and we end up taking the one that governs. So on that load combination homework, you remember we computed a bunch of load combinations, and what I was interested in is the one that was biggest, okay? Because that represented the biggest load on the section. Now I ask you, of these 3 values, which one do you think I'm interested in for the purposes of design? Like if I asked you what the net area was going to be, which one would you use? The lowest number, exactly, because the net area is a function of its strength. If I take this section and I yank on it, where is it going to fail? It's going to fail along the path of least resistance. And how do we determine the least resistance? It's the path with the smallest area. This is the one that governs. So the net area in this section is 9.697 inches squared. That's the answer. So like on the load side, we're always taking the largest load. Now, what Mr. Blizzard said seems like something we can eyeball. In fairness, in a lot of cases, that is correct. There are some specific cases where that isn't that doesn't happen. And we're going to look at one probably later. Not right now, but we are going to look at one later. What I'm interested in right now is that you can navigate the math and that you can identify all of the possible failure paths. So I know we're running short on time, so I do want to pull something up real quick. I want to show you your homework. Man, my camera has like officially froze. I don't know what happened there. I'm glad I'm recording this locally because locally I'm having a problem. So can everybody see the homework that's popping up? So, all right. So this one, you know, pretty much all of the bolts are lead line bolts except for G. G is the one bolt that does not occur on the lead line. So on this connection, I want you to determine the net area, but I also part of this is about recognizing the patterns, and I want to see if you can identify all of the possible net area paths. And I will tell you, there's actually quite a few of them. I think that there's maybe 12 different paths, but a lot of them repeat because of symmetry. I might be getting my count wrong on that, so don't quote me on the numbers. But I want to see if you can identify all of the paths, and then I want you to determine the net area for this connection. Now, as Gordon said, it seems like something you can eyeball for connections with symmetry and connections that are fairly simple geometrically. Admittedly, this is true, but sometimes there are instances where it is not so simple geometrically. The simplest example I can describe verbally, and then I'm going to call it because I know we're running out of time, but if you have an angle, a piece of angle iron, you know, like an L shape, and there is a stagger that crosses the legs, so it's a staggered connection across the legs, then sometimes it's not that easy to determine the net area because you have to sort of turn it into an equivalent plate and find the net area that way. It's a little tricky, but we'll handle that later. I want you to do this one problem, see if you can determine the net area. That's due Monday. That's all I have, everybody. I will see you all on Monday. You all have a wonderful weekend. All right. We'll see you then.